So this is going to be a little bit of a funny talk. I don't know if you're going to learn any like exciting new programming techniques or anything like that, but my hope here is just to kind of show you something really fun that I've been doing with Clojure lately, and hopefully inspire somebody to play around with some of these things. So the topic of the day in particular is MIDI and doing MIDI through Clojure and making music. So real brief about me, since we just talked about some of these things. I run a Clojure startup myself. I've been in Clojure space for quite a while, maybe 8 years at this point. Still learning things all the time, still love it. I am not a very good musician, so don't expect much from me on that front, but I'm excited about the ability to interface code with music. Based in Austin, used to live in Taiwan for a while, so a little bit of an Asia connection there. I am going to be at the con, so if you're going to be there, please say hi. If not, let's connect online. So MIDI, I'm sure some of you are loosely familiar, but really it's just a very simple standard for encoding digital music, right? So there are a lot of hardware devices that speak MIDI. There are a lot of software devices that speak MIDI. They can all interact very nicely. And it's a nice, simple format that's pretty easy to understand, at least at the basic level. So it just encodes notes as integers, kind of in an arbitrary way. But as I'm showing here, like just the integer 60 is the note that is typically like middle C on a piano. I like to think that MIDI is kind of to wave format as vector graphics are to raster graphics, which is to say that it's a lightweight encoding that is more about specifying the basics, not about any particular way it actually comes out sounding, right? So the same MIDI notes can be played on different synthesizers. They sound different. They can sound like a piano or a drum kit or something else entirely, square wave, I mean, anything. And in that way, it's really lightweight and it's really flexible. And I think MIDI is really fun to play with Clojure because, basically a song is like something like a sequence of integers. I'm simplifying a little bit, but when you think about all the great sequence abstractions we have in Clojure, how easily we can handle those things, I think it's a really nice fit between the two. So MIDI is used for input and for output. You can do this totally without a computer in the mix at all. You can take a MIDI keyboard, you can plug it into a MIDI synthesizer, and generate music from there. But more commonly nowadays, people route it to their computer, and then of course you have a host of software that you can use to do a number of things, and I'll show you a few of those in a little bit. As I mentioned, the basic notes are just encoded as integers. There are a few more things to the standard, like channels, where you can separate notes into different streams. Those channels are again just specified by integers. We'll cover this a little bit in a minute. Notes can also have velocity, which is typically a representation of how hard that note was played on the keyboard or the drum pad or whatnot. And then there are also these system messages called sysx that are really vendor specific, and they mean that the format's really open to extension by hardware vendors to do all kinds of stuff. So I won't belabor much of that. We're not going to dig deep into most of those things, but just wanted to let you know that they're there. As far as how you do MIDI from Clojure, the cool thing about MIDI is that when you plug it into a computer, your operating system really acts as a MIDI bus, right? So messages are sent by devices. Any other devices can subscribe to those messages. It's kind of a pub-sub story in a lot of ways. So you can listen to any device on the system and kind of, from whichever side of that you want to do it, whether you want to be an input or an output, it all just kind of plugs into one unified hub on the system. So there's a library in Java that is specifically made for working with MIDI. That's this JavaX sound MIDI. And it's really not too bad to use on its own. But one piece of complexity with it is it has some native code. So your JVM on your operating system has some probably C code that interfaces with the kernel to provide some of the capabilities. A lot of these other notes here aren't super important unless you really want to dig into this and do it yourself, but I wanted to make sure I captured it. So there are some flaws in the implementation on Mac OS. Took me about half a day to figure out what was wrong and find that there's a replacement library you can use that does work. So do note that if you're playing around with this stuff on Mac OS. Finally, there's a library out of the Overtone project, this MIDI CLJ library that is really, really convenient for doing this kind of thing that you'll see in a minute from Clojure. But it also has the same kind of problem I ran into getting it to talk to my DAW, which I'll cover in a sec. So again, be aware of that, and I'll show you how I did that. So one last thing is that when you want to have software generate MIDI messages and make those available to other devices on your computer, you need to have basically a virtual MIDI device that those programs can read from and you can send data to. The process to do this on macOS is super easy, which is awesome. It's basically built-in functionality in the operating system. So you can really easily just wire up Clojure to start sending out this data and then plug it into anything you want, which I'll show you now. So let me go here. All right, so this is Ableton. Ableton is a DAW, which is a digital audio workstation. So just a piece of software made for making digital music, essentially. And it can record really like wave style, I don't know what to call that, but what I was previously calling rasterized kind of audio streams, or it can record MIDI. And so I'm going to change my display a little bit, and I'll show you. Interesting. My cursor is captive here. Okay. So can you see that? I have a couple of devices on my desk. And
Yep, you can see it.
awesome. Okay. So basically, I wanted to show you just kind of a simple MIDI keyboard setup over here. And then this is called a Launchpad Mini, which is basically like a drum pad. And so in Ableton, we have these tracks, which are the columns, right? And if we look at this one, I'm saying to take MIDI from this device called Launch Key MIDI, right? And so if I play on the piano over here, can you hear that?
Yep.
To make sure we're working. Awesome. Okay. So, yeah, it sounds like a piano right now, but like I said, it's not truly tied to any particular instrument, right? So we can change this out. We can say, I don't know, we want it to be a bass instead of a piano. Doesn't sound like a bass, but some kind of bass sound, right? So again, it's just kind of this simple description of notes rather than a particular instrument. So then over here on the other device, I'm sorry, I wasn't showing you my screen while I did that, so there you go. Over here on my other device, I have this wired up to this first track right here, which is tied to a drum pad at the moment. So each of these 16 pads in the bottom left corner will make different percussive sounds, right? Okay, so this will be important in a minute, but if you look down here on my screen, these are basically these drum samples that are tied to each of these pads. And you'll notice that when I push one of these, there's a little light down here, right, that lights up in accordance with the note that is tied to the drum. So basically, this is kind of a spectrum of all of my MIDI notes, and these 16 master sounds outside of this range, there are no sounds mapped, so you don't hear anything. So just wanted you to know the basics of kind of how a DAW works, so you can see how I'm generating the sound that we're going to generate from code in just a second. And so I mentioned earlier that we need a virtual MIDI device in order to be able to have our code generate sound within DAW. The way that we do that on macOS is in this audio MIDI setup program, which is just a built-in program. You can actually go in here, do this show MIDI studio thing. And this device, which you can just enable, is a virtual device that we can talk to from software. So once we've done that, then we can make a new track. We say, okay, now we want to get the audio from that device, that virtual device. And then in the same way, we can set up an instrument on it. And so I have a grand piano set up on this. So now we're ready to write code that actually generates sound from MIDI. So I'm going to hop over to Emacs. Don't need that. Okay, so in my depth studying, I just have these two things, which are the two libraries I mentioned earlier. This is the one that is the fixed version of the macOS MIDI functionality. This one is that overtone MIDI library.
By the way, Cameron, the top of your screen is cut out a bit. So we can see one of the libraries, but not the very top. Yeah.
Okay.
Yeah.
You see the top now?
Yeah.
Excuse me. Okay, cool. Let's see. Go in here, start up a REPL. Excuse me. Sorry, just getting over a cold. Okay, so the first thing I want to show you is how we discover the MIDI devices, excuse me, that we have on the system. So using this overtone MIDI library, we can just run this function, and we get back a bunch of maps that describe these devices. So you can see that each of them has a name. And that's how we find the device that we want typically. So this library has some convenience functions that help us just find things by name, and specifically find like an input device or an output device by name, right? So here, I have this device, this launchpad already defined here. So all I have to do to get that device is just run that. You'll see the only thing in here is that map that specifies the device. But this is everything that Clojure and under the hood Java need to find that device and send messages to it. Excuse me. The launchpad that I showed you earlier, which is this one down here, you notice that when I push those buttons, they light up. That's actually not built in. This thing actually functions as both an input device and an output device. And I'm making those light up by actually routing the input notes back to the output, and that is what triggers the lights. So one of the really interesting things about MIDI is it's actually used sometimes in concerts to control lighting, to control pyrotechnics, all kinds of stuff. And all of those are actually just based on certain notes telling it to do certain things. When I send a certain note, it just does some number. Sending that back to the output device makes that light up. And actually the velocity of the note, which typically represents how hard it was pressed, changes the color on this device. So it's really just using these two integers to light up. So I'll show you that. So here's the basic way that we can use this library to get inbound events. So we tell it the name of the device we want, or the map, sorry, that we want to get the events from, and a function to invoke every time a message comes in. So here I'm just going to pretty print these. So I turn this on. Let me make a quick change over here so we don't hear a bunch of sounds as I do this. And now we'll come back. Okay, so now I'm just going to hit something here, and you see we get this map. We actually get two maps, and the reason is that the first one is a note on message, and the second one is a note off message. So we can see what the note number was, what device it came from, the velocity, which is actually hard coded on this thing because it's not velocity sensitive. And like I said, we get this note off when I let up on it, right? So you can see the distinction if I hold it and then let go. And the note off has velocity 0, which is part of how that's signified, I believe. So with just this, we can get input from any MIDI device, which is pretty cool. With its weird incantation, we can tell it to stop printing these. So here, I'm going to send MIDI notes, but this time I'm going to send them to the output device, which again is the same physical device, but it's the lights. Essentially, it's controlling the lights. So I have some convenience functions in here that really just map from the MIDI numbers to the coordinates on this grid, calling this 00 and this 88. Right? And then I know the constants for the colors, but again, they're just velocity numbers. So with that, which didn't immediately work, let's see. Oh, I actually number them from, this is the origin up here, I'm sorry. So you see that this came on, it came on in the color green. Now I can send a note off message to turn that off. Similarly, this allows you to specify a duration and then it turns off. So I'm setting for 500 milliseconds, turn that on, and turn it off, so half a second. And here we can get a little fancier, and you can see it's kind of running a series of lights down this thing, right? So I thought this was pretty fun and kind of just kept digging deeper and deeper on it, which you'll see in a little bit. Here's just playing with the velocity. You can see kind of all the different colors. So that is MIDI output. And I think if this thing were a synthesizer instead of this, you know, we would actually hear sound, right, in accordance with the notes that we're telling it to play. But here we're doing something really different that I think is pretty fun, kind of using this as a low resolution display. Slightly more complicated example, not much more complicated, tying it together. So here we're going to handle MIDI events that come in off this device. We're going to look at those messages, destructure them, figure out if they're note on or note off messages, and then basically send a corresponding message to the output, which just means that we're going to light up again when I touch it, right? And, you know, it's multi-touch. I don't know how many can actually light up at once, but quite a few. So that's kind of the basics of tying those two things together. So I'm going to stop that and then move on to something that actually has sound. So a couple notes in here on the things I discussed earlier, that this overtone is not really built to support these timestamp messages, which is just a quirk that this DAW expects. So I kind of had to hack the definition of some of these functions to make it work. The right answer, of course, would be just extending this library properly and submitting a pull request or something, but I haven't done that yet. So here, I guess I'll recap. In the last demo, we were just dealing with this device directly. Now we're going to deal with the virtual MIDI device that we created, which, if you recall, was named IAC driver. So we have this name, use this function to find that device. Looks like that. And then basically, I'm going to generate some scales. So if you know some basic music theory, you know that major scale and minor scale are just defined by a series of whole steps and half steps that repeat, right? And they're only slightly different, actually just shifted by a couple notes. But so I represented that pattern of kind of whole steps between notes and half steps as just ones and zeros. And then with this pattern that defines the scale, we can take a sequence of all notes and transform it into a sequence of the notes in the scale. And so we can do this on an infinite sequence. It's a great simple example, I think, of Clojure's strength in dealing with sequences, right? So all we do is we cycle that scale, so we make an infinite sequence of these, and then we basically just take the sequence we got and we say, hey, if it's a 1, we're going to keep this note. If not, then we're going to throw the note out, right? So here, we'll see if I'm set up right. Okay. No. Right. So again, this is my IAC driver, my virtual MIDI device. Has a grand piano on it on the moment. So I'm just going to play a note here to make sure it's working. Cool. And so here, just so you understand what this is saying, this is note 60, which again is that middle C, and then you can see down here I pass it a velocity, which is just kind of how loud to play it, and a duration. So we're going to play that for half a second, right? So here we're going to take all the numbers, drop 60 of them, meaning we're going to start at that middle C, and then take the next 2 octaves of notes, actually one more than the next 2 octaves, but either way. Then we apply our scale notes function to actually get the notes that are in that major scale, right? So you can see it would just be these notes according to this pattern here, basically applied twice to the range of integers. And so if we play that, now you can hear we're playing a major scale, or similarly, swap that out for a minor scale. So we have some real basic kind of music theory foundations. And then similarly, when we're working with drum pads, again, they're just notes, but instead of being pitched, they're applied to samples. So in this case, this is intended for putting on one of these drum kits. And then this is probably a bass drum. Okay. So this is going to do something similar, just run over all the 16 instruments starting from the first one. Cool. So, that's really all it takes to start making sound, let's say, from Clojure code, right? All right, so now I want to show you this, which is where I kind of took all of this to the limit. And I'll demo a little bit of this and then probably flip back and forth into the code as I go and show you how some of this works. So again, we have this launchpad device. We're using both the input and the output. And this thing that I built is essentially a framework for building little software instruments or visual demos or all sorts of things on this device. So The way that I've set this up is when you first started it up, it does this green, that's supposed to be like a green traffic light. I'm sure you can tell that's a circle. And so it's kind of just in a drawing mode here, right? So we can just light up whatever we want. And then, and just so you know, I'm using all the same basic tools I just showed you to monitor the messages as they come in and then send new messages out. And I'll show you that code in a second. And then these buttons on the side are also just other numbered notes that we can get access to. So one of the things I implemented is down here. This is what I call the options mode. The O indicates options. So we come in here and do a few different things, but one of them is we could change the color that we're currently painting with. So, all right. Crazy, I know, like just using what's intended as a music device as a display device. But I was having fun with this and just thought, you know, how far can I take this basic idea and what can I do with it? So let me pause there and show you just a tiny bit about the internals. So one of the things you can do from this options mode is turn on in debugging mode. And when we're in this debugging mode, it basically dumps its internal state. And you can see that the state of this thing, for example, this line, is just a map, right? And there are a couple interesting things in here, but I'll ignore that for the moment. So this is the whole internal state of everything that's happening here. So what I'm doing is every time you tap a note, it sends a message over MIDI. The MIDI is received, and then we run a transformation on this map. And the new map that's returned becomes the new state. A lot of those transformations just change this board. You know, which is just a bunch of integers representing the possible colors that we could display. And then we throw a few other things in here, like this color is kind of what color I chose I wanted to paint with. This mode is kind of which of the side buttons I hit. You know, really anything you want. It's fully extensible. And I'll talk about these in a second. But so let's go into that code. Okay, so all of these modes are just defined in a map as well. So the first mode I told you is that paint mode. And so there are actually just a series of callback functions in here that get triggered on certain events. And so this one is the simplest of all. Really the only important thing it does is on tap, which is just a defined callback function in this little framework, it runs this paint function. And the paint function, all it does is kind of exactly what you would think, right? It goes into the state, it updates a slot in the board to be the color that is the active paint color, or it turns it off if it was already on, right? And so it's just this very simple little atomic function that does that, right? And so all of the like on tap functions just take a board and return a board, and that's all it takes. So after I did this, I was like, okay, it would be interesting to incorporate a notion of time into this. So I made this kind of silly mode where you hit this and it turns on gravity. And so these things just fall if there's nothing below them, right? And you can paint still and it just kind of falls down, right? And you know, if you look at how this is defined, again, there's this paint function exactly the same that I used above. And then there's this on tick function. So I introduced the concept of kind of a game, you know, clock, almost like a game engine. There's a tick every certain number of milliseconds. And then all we need to do is run this gravity function, which is a fairly simple little function that is just based on the state of the board. So it looks at the state of the board and makes changes according to what it needs to move down. And again, this is a function that takes a board and it returns a board, right? Now I showed you that the full state of the whole thing, of the world, let's say, is a map that contains a board and some other things. So since this doesn't take the whole world, it just takes a board, I have a little helper function that lifts one of these functions that goes from a board to a board into a function that goes from a full state to a state. Hopefully that makes sense. It just makes it more convenient to write these things, right? So let me show you a couple more things, and then let's see, it'll be done before too long. So, I started playing around with what other fun stuff could I do by composing functions that manipulated boards. And so one of the next things I made was this rain thing. So just generates random blocks and makes them fall. But what I thought was kind of cool about this is I already had this function that implemented the gravity part, right? So all I actually needed to add to that was something that generated random blocks in the top row, and then they would just fall, and a fader for the bottom, essentially. And so, I really liked how that composition came together. You write these little functions of boards, literally just call comp on them to combine them, and then you have this more interesting, more complex thing, right? So took it a little further, and then I said, well, it would be cool if you could do Conway's Game of Life on this thing, right? Like I already have some kind of state that was either generated by something I was running. By the way, I just paused that and I can keep drawing, turn on gravity, go back to rain, whatever. But I already have these randomly generated states on this grid. It would be cool if we did cellular automata on this thing, and what would that look like? So, I don't know if you guys are familiar with Conway's Game of Life. If not, look it up. It's super cool, but it's a cellular automaton. It's basically a very simple set of rules that leads to complex emergent behavior, like sometimes finding interesting stable patterns. And so I implemented this. Again, it's just a board function. It has no external state. It's just looking at what was the state of the board and making a new state of the board. And then one of the things I did with it that's kind of fun is that in the traditional Game of Life, there's no concept of color, right? So here I've colored the blocks according to what rule in Conway's Game of Life generated that block, which I thought was kind of interesting. And then if you're very familiar with Conway's Game of Life, you may know that there are some particular kind of famous patterns that have names because they do interesting or unique things. This, I think, is called a pulsar. It's kind of a semi-stable pattern. But a more interesting one is like this walker, which kind of alternates between a couple different patterns that allows it to kind of move itself across the screen, which I thought was kind of cool. So if that's not weird enough for you, I'm going to take it one step further. And so I wanted to get back into playing with actual music in this device, and thought about, okay, how could I combine kind of all of these things, right? So let me check what instrument I have set up in my software real quick, and then I will show you this. Okay, cool. So there's another kind of hidden option in here, and all this does is when the bottom row of blocks are lit up, it plays a note over MIDI, and it'll go to Ableton here. And so then that's another function that I could compose with my others. Obviously, it's side effecting, so a little bit different. But so now you can kind of ask yourself questions like, what would rain sound like? And that's a very low pitch, right? But let me pitch it up. But or what does life sound like, and when it hits this edge, right? So I thought that was kind of a fun little hack, but then took it a little further and did something that I think is actually kind of cool. So this is a mode I haven't showed you yet, but it's built on that same function of like when something hits this bottom row, we're going to play a note, right? And this was actually more like a software synthesizer toy, let's say. But basically, what it does is it makes these kind of bouncing balls, right? And so there's just a function that makes these bounce. It has to keep a little external state so it knows what the frequency is, but we're just relying on the same rule to play a sound when it hits the bottom. So now that we have that, my time is off, but we can basically we have a little drum machine here, right? Hopefully you can hear that.
Yeah, we can hear. You can hear that.
Awesome.
I think you can move up the launch pad a bit up.
Oh, sure. Anyway, that's the basic concept with that, and I just thought that was fun. It kind of emerged from these different things that I was playing around with, and just made me think a lot about the different ways that we could pretty easily define tools that use Clojure, to make music in different ways, right? Like all kinds of new and interesting ways, and that was not many lines of code to make what's essentially a simple drum sequencer. And of course, there's no reason why that has to be a drum machine either, right? I mean, we can use that to play melodic music. And one of the things that is pretty cool about working with MIDI is that when you have these notes coming in, it's very easy to transform them in real time into different notes, right? So let's say we're just playing this, and over here I can pitch this up an octave if I want, right? Like maybe that's too low. And then maybe instead of playing individual notes, we actually want to play whole major chords. So this is actually going to make triads out of those individual notes. And again, all these things, just compose pretty simply, right? So we have a pretty interesting kind of interactive environment to be able to find stuff here, to find stuff there, and make something really interesting. And of course, also, as these come in, we can record all of those notes, we can edit them in the DAW. Like the sky's really the limit. So those are kind of the basics of what I wanted to show you. I'll just show you a couple more things in the code briefly, and then I'll wrap up. But so everything you saw, is defined pretty simply in terms of really just maps, sometimes maps of maps, right? But these simple callback functions, these little transformers that either go from a board to a board or the whole state to a new state. And I mean, even this options mode, which is kind of the ugliest thing here, still kind of just defined in terms of these basic primitives. Here, this defines which modes these side buttons on the right-hand side of the device map to. And let's see. yeah, this is just utility stuff that's all pretty simple. A couple fixed patterns, you know, an empty board. It's kind of what you'd expect. Uh, and then I'll show you just briefly. This code is a little messy. It needs a little bit of cleanup, but you know, just in terms of how this whole thing works, it's actually pretty darn simple. So we start with an initial state, and then the state is stored in an atom. And I have a watcher on that atom that says anytime this atom changes, we redraw the board, right? There's a little bit of debugging junk and optimization in here, but basically we watch the state and then draw the board. And that's basically it, right? And Atom Watcher's made this very easy to do. And then there's a separate thread running down here, which is the main reason some of this looks a little weird is there's this feature to run this other thread that is for these tick messages that we're running on a regular basis. But really, every time we transform the state, we're just doing a swap on the state and running one of our kind of handler functions based on the current mode. And then finally down here, we watch for MIDI events and handle those with this handle message function that is a little big, but not that complicated, really. And again, it's the same kind of thing. It's like if we tap a button on the main grid, we see if the current mode has an on-tap handler. If it does, we're going to run that and let it know where they tapped. And that's kind of it. So anyway, you know, it's mostly a day's work here, so it's not, I mean, it's not perfect, but it's not anything too complicated. I can tell you it's a blast to play around with. So that's kind of my little project. So yeah, I guess that's it. Let me switch back to my camera.